Good evening, everyone. Today we'll be discussing little bit more interesting astronomy than earlier days. So today we'll be discussing little bit about the photometric calibration. It is very important. Suppose you have observed some stars with your telescope, with your detector. After that, you have reduced your data and you got the instrumental magnitude for that particular object, but that is instrumental magnitude, that is not standard magnitude. Now there is a process how to transform that instrumental magnitude to standard magnitude. Okay, it is very interesting. So before I start, I want to ask you one question. If I consider that our Milky Way is made of only stars, there are nothing, only stars, then what will be the volume filling factor? Do you have any idea? How much volume of our Milky Way is covered by the sun-like star? Do you have any idea? Any idea? Do you have? Okay. Okay, let me start. Yes. So I think you have no idea about that. So if we consider that our Milky Way, it is a stellar system, it is made of only star, then what will be the volume filling factor? You can calculate what will be the volume filling factor. This F, it is nothing but volume filling factor. It is V star. V star is nothing but the volume of sun-like stars. This V is the volume of our Milky Way galaxy. Roughly, if we consider that all stars are sun-like star, then radius will be nearly 700,000 kilometer, and there are nearly 10 to the power 11 stars in our galaxy. Then the volume will be nearly 1.43 into 10 to the power 35. So in the same way, if you try to find out the volume of our Milky Way galaxy, if you consider it is a cylindrical in shape with nearly 100,000 light year radius and 10,000 light year height, then the volume of our Milky Way galaxy will be nearly 2.6 into 10 to the power 53. So what will be the volume filling factor? You will surprise. You see, volume filling factor is 5.5 into 10 to the power minus 19. It is nothing. It is nothing. Now the question is, then what else are there in our Milky Way galaxy, right? So generally the medium between two stars or medium between any star and you, we call it as a interstellar medium, right? So that means our other volume, the remaining volume of our Milky Way galaxy is basically covered by the interstellar medium. So now the question is, what are the contents of our interstellar space or interstellar medium? First of all, radiation. Radiation, it is stellar radiation as well as cosmic background radiation, and energy density is nearly 1 electron volt per cc. Next one is cosmic rays, right? Cosmic rays, for cosmic rays also energy density is nearly 1 electron volt per cc. Third one is magnetic field. You see, our galactic strength of the galactic magnetic field is very small. It is nearly 5 microgross, but still it is playing a very crucial role in astronomy. Without magnetic field, we cannot imagine our Milky Way. We cannot imagine any celestial object in this universe. And the energy density is 1 electron volt per cc. And fourth one, which is very important, that is gas and dust. Gas and dust. Generally, the ratio of gas and dust in our Milky Way galaxy is nearly 0.006. Okay. So what is the density? What is the density for gas? It is nearly 1 hydrogen atom per cc. And this is nothing but the energy density, 1 electron volt per cc. So now, if you consider the dust, so nearly 1 to 4% of the interstellar medium is covered by the dust particle. And the temperature of dust particle is very low. It is nearly 50 to 100 Kelvin. Okay, and the average size of the dust particle is nearly 0.55 micron average size, but it is starting from 0.1 to 0.6 micron. Now we came to know about that. So these dust particles are generally paramagnetic in nature. These dust particles are paramagnetic in nature, and since it is paramagnetic in nature, it is generally, these dusts are made of silicate or calcite with a ice mantle or polyaromatic hydrocarbon mantle. Okay, so this is nothing but the dust particles, and the dust particles are basically not spherical in shape, because this dust have also spin. So because of the spin, these dust particles are aspherical. It is not spherical. Since it is aspherical, so this dust particle produces selective absorption. Okay, this dust particle produces selective absorption. So this dust particle played a very crucial role about our understanding of the universe. Actually, for me, what I feel, actually our knowledge about our universe is limited by the dust particle. Now we will came to know how. So now we see in the year 1904, the famous astronomer Hartmann, it was published in FEJ, he has observed Delta Orionis. It is a type B1 star. It is an eclipsing binary with a period of 5 days, 5.73 days. And it is an eclipsing binary. So one star is eclipsing around another star. So what will happen? If you try to find out the radial velocity of some prominent line, then what will happen? When the star will coming towards you, radial velocity will be increasing. If it is moving away from you, then radial velocity will be decreasing. So he has done spectroscopic observation. From spectroscopic observation, he find that hydrogen, helium, ionized magnesium, etc. in the spectrum of Delta Orionis varies from plus 135 to minus 79 kilometer per second, which is obvious, which is we are expecting that result. But there is a line of ionized calcium, which is ionized calcium K line, and the wavelength is 3933.7 angstrom. And he found that this line is stationary. Though he is observing an eclipsing binary, this line is stationary. It is not changing. Radial velocity is not changing. It is plus 16 kilometer per second. And he also found that the absorption lines are very narrow. Generally, in case of star, you know, inner sphere is photosphere, then chromosphere, then corona. When the proton from photosphere just came out, then what will happen? Because the temperature of your corona is low, so it produces absorption lines, and the photospheric absorption line, width of the photospheric absorption lines are generally thick. It is not narrow, but the width of this stationary lines, calcium K line, width is very narrow. Then Ostrov in 1929, he also found that the line strength increases with distance. Line strength increases with distance. It is a very interesting fact. So if the line strength increases with distance, then it should not be a circumstellar line. Origin should not be a star, right? So after that, you see, in 1930, R.J. Trampler, he has published this paper in League Observatory Bulletin in 1930. Okay, what he has done, he has observed numbers of open cluster, and from the intensity of that open cluster, he tried to find out the distance. We already know intensity is inversely proportional to square of the distance, and from this distance, what he tried to find out? He tried to find out the angular size of the clusters. So angular size is nothing but D into cluster size is equal to D into angular size of the cluster. So what he found that more distant clusters are appear to be systematically larger. Distance is increasing, that means size of the cluster is also increasing. It is very interesting. It should not happen. It should not happen. So what could be the reason? Later on, he found that this is nothing but this is due to the interstellar dust absorption, scattering by the interstellar dust. And he found that the value of extinction is nearly 1.6 magnitude per kpc. You see, your dust particle absorbs as well as scattered the light which are coming from the open star cluster. And you know, intensity is inversely proportional to the distance. So this intensity is already tempered by the interstellar dust, and so whatever distance he is getting, it is not the true distance. So that is the reason why distance clusters appear to be systematically larger. So this is the starting point. This is the starting point. From observation, people came to know that interstellar dust always absorb. Okay, so this is nothing but interstellar extinction. Now let us see. So now the question is, when the light from any celestial object passes through the interstellar medium, then because you know the size of the interstellar dust particle is varies from 0.1 to 0.55 micron or 0.6 micron. So what will happen? It will absorb some amount of light as well as scattered some amount of light. Some wavelength will be scattered and some wavelength will be absorbed. If it is absorbed, then it will be reddened. If it is scattered, then it will be goes off. Okay. So this is the reason why interstellar extinction plays a very crucial role in astronomy and astrophysics. Now we will discuss about this interstellar extinction effect little bit later. Now let us introduce another effect that we call as a atmospheric extinction. All of you know our atmosphere is also, our Earth atmosphere is also full of dust particle, ions, molecules, atom, etc., etc. So when the light from or electromagnetic wave from any celestial object enters inside the Earth atmosphere, then what will happen? The dust particle, atoms or molecule which are present in our atmosphere will scatter and absorb some amount of light which is emitted by the celestial object. So now you understand. So the if you try to calculate the magnitude of that particular star above our Earth atmosphere, then it will be different. If you calculate the magnitude of same star from ground-based observatory, then your magnitude will be different, because if the star is emitting 100 photon per second, so above atmosphere it may be 100 photon per second, but at the ground it may be 40 photon per second or it may be 60 photon per second, because some number of photon is already extincted by your Earth atmosphere, right? So what we have to do? So you know how to calculate the instrumental magnitude. You already know that is minus 2.5 log 10 f by exposure time. So now what we have to do? We have to convert the instrumental magnitude, which is measured on the surface of the Earth, to the instrumental magnitude that would be observed above the Earth atmosphere, right? You understand? So what we have to do? So now you see, now just look at this figure, and in this figure what we have done, we have considered some assumption. We assume that the atmosphere is a series of thin parallel layers like this. It is thin parallel layers. Okay, and let us consider a layer. We are considering this layer of thickness dx, and altitude of this layer is x, right? And this angle z, we call this angle z as a uh, we called it as a zenith angle. We called it as a, this z we called as a zenith angle. Okay, so the value of zenith angle at your zenith, this is your zenith, at zenith it will be 0, and the value of zenith angle at your horizon, this is your horizon, at your horizon it is 90. Okay, so that means the angle will be increasing from zenith towards the horizon. Zenith 0, so if you are coming towards the horizon, then it will be 90 degree. Okay, so now if if I'll try to find out the path length, this is nothing but the path length in this layer. So the path length, the value of path length will be simply dx into sec of z. Dx is nothing but this thickness, and sec of z, this z is nothing but your zenith angle, right? And this sec z, sometimes we represent this sec z as a x also. This sec z is nothing but air mass. We called it as a air mass. So now at zenith, your zenith angle will be 0. So the value of sec z will be 1. So at zenith, the value of air mass is 1. So now if you are moving away from zenith towards the horizon, then what will happen? Your air mass will be increasing. Now you see, if you are at zenith, your starlight will passes through this much area. But if you are increasing the zenith angle, then you see the path length will be increasing slowly. If path length is increasing, that means your extinction is also increasing. Scattering and absorption is also increasing. So that means your extinction is nothing but a function of air mass. With air mass, your extinction is changing. You understand that now? So now if your zenith angle is 60 degree, then your air mass will be 2, right? But if you increase your zenith angle more than 60 degree, then what will happen? Then there will be a problem. Initially, what we assume that our atmosphere is a series of thin parallel layers. But if you increasing your zenith angle more than 60 degree, then what will happen? The plane parallel approximation breakdown. Your layer will not be parallel. So the curvature of the atmosphere start playing role because of the refraction, and diffraction. What will happen? The curvature of the atmosphere will start playing role. So initially we are using sec z. We are using sec z as a air mass. Now you cannot use this sec z as a air mass because sec z is valid only for the series of plane parallel layers. But now your layers curvature is already added if you increase your zenith angle more than 60 degree. So during the time of observation, sometime if you go for observation, never observe your object below 60 degree. If you observe your object below 60 degree, then extinction will be very high. So in that case, you cannot use this simple sec z. So instead of sec z, what you have to use? See, instead of sec z, you have to use, this is nothing but your air mass. I have already mentioned. So initially your air mass was simple sec z, but now you have to use some other correction factor. Those are generally sec z is equal to 1 minus 0.0012 into sec square z minus 1. Now you have to use this one. So be careful when you go for any observation. Always it is better to avoid the objects which are below 60 degree. Or you can go up to 45 degree. You can go up to 60, so 30. Yeah, 60 is enough. I think 60 is enough. Below 30 degree, you should not. You should always avoid. Okay. So now the question is how I am going to find out the value of extinction coefficient, right? What is extinction coefficient? Because that is required. That is required. So what I have to do, uh, uh, just to calculate the extinction coefficient, we have to select some photometric standard star like Vega, A0 type star, right? Like Vega, because these are photometric standard star. This is known to us. Okay, so we have to observe that kind of photometric standard star starting from east to west, starting from rising to set. Okay, so now what you have to do, certain after certain interval, what you will be getting, after certain interval you will be getting instrumental magnitude of that star as a function of air mass. At zenith your air mass is 1. If it is, if zenith angle is increasing, then your air mass is also increasing. If air mass is increasing, then your extinction is also increasing. So there will be effect. That extinction effect will affect your instrumental magnitude. So now after that, what you have to do, you have to make a plot between air mass, this is air mass x, air mass versus apparent magnitude. Okay, if you make a plot air mass versus apparent magnitude, then your point will be coming like this. And after that, what you can do, you can fit a straight line. You can fit a straight line on all those data. If you fit a straight line, then what will be your expression? Your expression will be m is equal to k sec z plus m0. This m is nothing but your magnitude. Okay, this is instrumental magnitude, and k sec z, this sec z is nothing but your air mass. This k, because y is equal to mx plus c, this k is nothing but slope of this curve. Okay, this slope k is nothing but the slope, and this slope we called as a extinction coefficient. This slope is nothing but extinction coefficient. And what is m0? M0 is nothing but the cut, this one. Okay, this m0 is nothing but the intensity or magnitude of that star above atmosphere. That is m0, right? So now you see, in this way, what you can do, you can observe your object in different astronomical filter, UV, VRI, all those filter, and then you can find out the extinction coefficient in all photometric band. But there is an issue. What is that issue? Let us see. If you observe your extinction coefficient, average extinction coefficient for each filter, then what will happen? The blue star would actually suffer from more extinction than corrected Thor, because blue star will be extincted more, blue light will be extincted more, and conversely a red star would be overcorrected for extinction, right? The solution is to introduce a color dependent secondary extinction coefficient, which generally known as K2, right? So initially we are using our instrumental magnitude to calculate the extinction coefficient. Now to remove all this color dependency, what we have to do, we have to make a plot between air mass versus color. Okay, if you, that is color index b minus b. If you go for that one, then the slope of that curve will be your color term, color extinction coefficient, that is nothing but your K2, right? So now your equation is, total correction equation is m is equal to k sec z. This is your magnitude correction, right? Plus m0 is nothing but the magnitude of that star above the atmosphere. So K2 is nothing but the color, C is color index, and sec z. So your equation will be a little bit different now. So this correction we call as a color correction. Okay. So generally, if you do photometry, if you do variable star photometry, if you try to find out very minute changes in magnitude, then all of you suggest you to go for color correction. But if you are observing a cluster, if you are trying to find out the magnitude of star in a cluster, not very precisely, it is not required to make the variable star light curve plot, then your first correction is enough. First one is enough. But if you are observing some variable star, if you are doing some variable star photometry, then you have to go for this color term. Now you see, this is the average extinction coefficient for natal sky. Okay, so now you see, these are your filters, UV, VRI. All of you already know UV, VRI. These are Johnson standard broadband standard filter, and this is the effective wavelength, right? And this is nothing but your extinction coefficient. You see, your extinction coefficient, it is a function of your wavelength, right? It is a function of wavelength. For shorter wavelength, your extinction coefficient increases. For longer wavelength, your extinction coefficient decreases. It is very interesting result. And you may ask me, what will be the value of your K2? The secondary extinction coefficient, that is K2, is usually of the order of 100th of a magnitude. It is very small. It is very small. Only for the accuracy of your measurement, you have to do that, right?
Sir, I have a question.
Yes.
This extinction coefficient, does it varies with the seasons, or is it constant throughout the year?
No. It will vary with the season. So especially during this time, your extinction coefficient will be higher. Okay. Generally, we the astronomer, best season for astronomical observation is sometimes starting from October to, you can say, up to January. That is the best season of observation. After that, your air will be polluted. There will be lots of dust particles. If dusts are there, definitely your extinction will be high. You won't get photometric night. Okay. So generally, during the time of observation, suppose today you are observing a variable star, in the same night you have to observe some standard star and you have to find out the extinction coefficient for extinction correction, right? So now next point, you see, this is 0 point. We called it as a 0 point. For 0 point correction, I'll tell you now what is 0 point correction. It is very interesting. If you like to do any astronomical photometry, these are you have to be very much expert in all these things. Okay, so there is a paper. That paper is published by Landlord in 1992. In that paper, you will find the numbers of UV-VRI photometric standard star. Okay, numbers of many photometric standard star. So for this kind of atmospheric extinction, you can pick up some photometric standard star from that Landlord, and you can go for the calculation of your extinction correction. Now let us talk about the 0 point. Suppose now you have observed a particular star and you have corrected atmospheric extinction. After correction of the atmospheric extinction, depth magnitude should be equal to the magnitude of that particular star above the Earth atmosphere, if it is correct 100%, right? But generally it does not happen. You won't get that. After atmospheric correction also, you will find some discrepancy between the above atmosphere magnitude and magnitude at the surface of the Earth. Why? Because you see, you are using some telescope. Your size of your telescope may be very big, it may be very small, and some layer of dust may be sit on the top of your mirror. You are using some detector, you are using some filter system. There may be some error in your detector optics, there may be some error in your filter optics, right? So now what you have to do, you have to correct all those error which are introduced by your filter, introduced by your detector, as well as introduced by your telescope. Then only your magnitude will be a standard one, otherwise not. For that, Generally, this correction we call as a transformation correction. What is that? How you are going to do that? That's very interesting. For that, what you have to do, you have to observe some, again, you have to observe some photometric standard. You can take some photometric standard from landlord. And what you have to do, you have to find out the magnitude of some particular star, particular photometric standard star. Okay, then you have to correct your value for extinction. And very important point is that since you are taking this photometric standard from landlord, so it is a standard star. So we know the standard magnitude for particular star. Just pick up the standard magnitude from landlord and try to find out the difference between standard magnitude and instrumental magnitude above the Earth atmosphere. So this difference, we call this difference as a 0 point for your magnitude. Right? Now, this 0 point, you can use this 0 point in your observation to correct your, just to transform your instrumental magnitude to the standard magnitude, okay, by applying this 0 point. Now you see the calibrated magnitude of the target star M can then be determined by simply adding the above atmosphere instrumental magnitude to the 0 point. So this is nothing but your standard magnitude. This is standard magnitude. So this standard magnitude is nothing but instrumental magnitude above Earth atmosphere. That means it is corrected for extinction plus 0 point magnitude, right? This generally we call this as a photometric calibration, 0 point calibration. This is very interesting. If you do any kind of photometry in astronomy, you have to do all these things. Otherwise, nobody is going to accept your data. You cannot publish your data in any journal. Nobody is going to buy your data. So it is very important steps. Now you see, generally we do two different kind of photometry. One photometry we call as a absolute photometry. What is absolute photometry? In absolute photometry, we use the photometric calibration for standardization. Okay, whatever I have mentioned, all these things, do extinction correction as well as 0 point correction. If you go for extinction correction and 0 point correction for your photometric data, then we call that photometry as a absolute photometry. But if you like to do absolute photometry, then your night should be very good. Photometric night or night condition should be very good. Seeing should be very less. Later on, we'll discuss about seeing. What is seeing? Okay. So there is another photometry. We call that photometry as a differential photometry. Generally, people who used to do variable star study, generally they use this differential photometric technique. What is this differential photometry? In differential photometry, along with the variable star, generally we consider a non-variable comparison star. So suppose this is the instrumental magnitude for variable star. What will add up for the instrumental magnitude for variable star? That is count for variable star plus count for sky plus extinction plus 0 point, right? In the same way, for comparison star is also count of comparison star, count of sky, extinction plus 0 point. All these errors are introduced in case of both the star. So now if you take the difference between your variable star and comparison star, then what will happen? This sky count, extinction and 0 point, all these will be cancelled out because I am taking the difference, right? So in that way, this differential photometry is very powerful. No need to do any extinction correction, no need to do any 0 point correction, no need to bother about the sky count, right? In fact, if your sky condition is not very good, in that condition also you can go for differential photometry. It is very powerful. Generally, for all variable star people, they use this differential photometric technique. But if you are going to do photometry for some other stars, other suppose cluster, galaxy, then nobody will suggest you to do differential photometry, because in that case, what you have to do, you have to go for absolute photometry, right? Now you see, we have already discussed about the interstellar extinction, right? I have already mentioned that interstellar extinction plays a very crucial role. It plays a very crucial role in our understanding about the universe. Now we see, generally, if we try to find out the apparent brightness of any particular star, then what will happen? There is a distance dependency, right? In addition to distance, also the interstellar extinction by the dust grain is also affecting the apparent brightness of an object. You already know distance, there is a distance dependency of interstellar extinction, right? Distance dependency of your apparent brightness. If you are going for absolute magnitude, then there is no issue. It is independent of distance. But if you are going for apparent brightness or apparent magnitude, it is a function of distance. Now you see, apart from distance, this interstellar extinction is also playing a very crucial role. In general, the more distant the object, the greater the amount of extinction, right? Already we came to know, because if we in case of Trampler, if he increase the distance, then size is also increases. That means extinction is also increases, because you see intensity is inversely proportional to the distance. So extinction is also inversely proportional to the wavelength, right? Extinction is also inversely proportional to the wavelength. As a result, the object is reddened, right? That means if you are moving towards the blue end, then your extinction will be high. If you are moving towards the red end, then your extinction will be less. So now the observed color index. Observed color index means what? Suppose you are observing a star in blue, in B and V filter, and after that you find out the instrumental magnitude for that particular star and in B and V band, and if you take the difference between B and V, that we call as a observed color index. So now the observed color index is increased relative to the intrinsic color index. What is intrinsic color index? Intrinsic color index is actual color index. Okay, this is observed, but this is standard. So intrinsic color index may be computed from the blackbody theory of radiation. By using blackbody theory of radiation, you can easily calculate the intrinsic color index. So this is my observed color index, B minus B observed. It is MB minus MV. MB is the instrumental magnitude in B filter, instrumental magnitude in V filter. Instead of your apparent magnitude, you can put here your absolute magnitude also, because you see we are using this formula. There is a ratio FB by FV by FB. So if you are taking the ratio, that means again, like that differential photometry, again distance dependency, there is no distance dependency because it will cancel out. For V and V, it will be cancel out. So in that way, this color term, this color index is nothing but it is independent of distance, right? So now you see, for perfect black body, by using black body radiation theory, you can try to find out the color index for perfect black body. It is minus 0.72 plus 7079 divided by T. T is nothing but your temperature. Now can you please tell me, should we consider our star as a perfect black body? Should we consider our star, whether our star is a perfect black body? Can you please tell me? Anyone? No, we cannot. We cannot consider our star as a perfect black body, because you see, uh, uh, if it is a perfect black body, then there should be only continuum. There should be only continuum. But in case of stellar spectra, sometimes you may get absorption features, sometimes you may get emission features. So you cannot consider our star as a perfect black body, but you can assume up to certain limit, you can assume it as a black body. Okay, for star, now for star, you can find out this color index. Color index. This is this color index. We calculate this color index empirically. That means empirically determined. That means determined from the observation as well as theory. So it will be a little bit deviated from the perfect black body. It is like that, right? So now what you can do, you can check whether your observed color index is equal to your intrinsic color index. It is not. Never. So now we are introducing another term that we call as a interstellar reddening. Interstellar reddening. It is written as E B minus V. B minus V is color index. So before that we use this E. We call this as a reddening. Okay, interstellar reddening. So this interstellar reddening is nothing but the difference between your intrinsic color index and your observed color index. Okay, this is reddening. So now you see, it is very interesting. From this reddening, what you can do, from this reddening, you can find out the value of interstellar extinction. How? The interstellar extinction and reddening is connected by the following formula. So AV is nothing but your interstellar extinction is equal to 3.2 into reddening, E of B minus V. What is AV? AV is nothing but the extinction measured in V filter, V band filter. So now you see, by applying this formula, now you can find out the extinction. So from your observation, you can easily find out this reddening, interstellar reddening, and after that, by applying this formula, you can easily find out the value of your interstellar extinction. If you can find out the value of interstellar extinction, then using your distance modulus, m minus m is equal to 5 log b minus 5 plus a. If you put the value of this interstellar extinction in that formula, by after that, by using that formula, you can find out the distance to that particular object. So this is nothing but your interstellar extinction. Okay, so it is very important. So again, I'd like to mention that this dust plays a very crucial role in our understanding about the universe. Also, if there is no dust, there is no star. Star formation is not possible without dust. If there is no dust, there is no star, there is no life, there is nothing. Okay, dust is there, so we are here today. So dust plays a very crucial role. So there is a very generally there is a branch in astronomy and astrophysics. Most of that we call as the interstellar dust, branches of interstellar dust. Many people works on that interstellar dust. I am also working in this interstellar dust. Okay, so now we will be moving to the basic astronomy part 3. Part 1 is complete, part 2 is complete. In part 2 we have discussed about all this photometric calibration. So now we'll discuss about the part 3. In part 3 we'll start with the telescope, then we'll talk about your celestial sphere and coordinate system. Then we'll be talking about the detectors, and then about the extremely large telescope, and some recent technique we are using, that is adaptive optics and active optics technique. Okay, so now you see, this is the first slide. In first slide, purposely I put all these figures. Okay, what is this? Can you please tell me what is this? What is this? All of you know this is nothing but a space telescope. This is Hubble Space Telescope. Okay, this is your XMM Newton. Okay, This is nothing but your millimeter wave telescope, right? This is your radio telescope. But can you please tell me what is this? What kind of telescope it is? What kind of telescope it is? Anyone? Do you have any idea what is this?
I think they are creating an artificial star and they are trying to measure some parameters.
They are trying to artificial star. What you are telling? What is this actually? What is this yellow line? Yellow these rays?
It's a laser beam. I think they are shining laser beam, and with that
Yeah.
they are trying to create some measure some extinction or something. I don't know, but it's
Yeah,
just a
yeah.
rough guess.
Yeah, your rough guess is correct. It is correct, 80% correct. This is nothing. This is you are absolutely right. These are laser rays, but there is a purpose of putting these laser rays. We'll discuss this about this laser rays when we'll discuss about the active optics and adaptive optics technique. Okay, so now the question is why we need all these telescopes. One telescope could have been enough to observe the electromagnetic spectrum which is emitted by a particular star, but it is not possible. Why? You see why? Now we'll be talking little bit about the atmospheric transparency. What is atmospheric transparency? In our atmosphere we have only two windows. One window is optical window and another window is radio window. For other region, for X-ray, for ultraviolet, for far infrared, for after that, our atmosphere is opaque. Our atmosphere is opaque. You cannot observe a X-ray photon or gamma ray photon or ultraviolet photon from a ground-based observatory. You cannot, because our atmosphere is opaque. So that is the reason why we need a space telescope. Why we need a space telescope? Because if you like to observe a X-ray which is emitted by a particular object, you cannot install your X-ray telescope on the ground because your atmosphere is opaque. So what is the reason basically? You see, you cannot observe a sub-millimeter photon. Why? Because this sub-millimeter photon is absorbed by the rotational level of molecule in the air. Our air is full of molecules, so that sub-mm photon absorbed by the rotational level of molecules. Far infrared photon is absorbed by the vibrational level of molecule in the air. So you cannot have. It will be absorbed by the molecules. Near ultraviolet or ultraviolet, it is not near ultraviolet we can have, but ultraviolet photon, it breaks up the molecules. Molecule absorb this ultraviolet photon and it breaks up. X-ray. What is the reason behind X-ray? X-ray ionizing the atom in the air. So all the atom absorb X-ray and they ionize. So your atmosphere is opaque basically. Gamma ray produces showers of particle and antiparticle in your atmosphere. So you cannot have. So that is the reason why we have only two windows. One window belongs to your optical range and another window belongs to your radio. Okay. So if you like to install a optical telescope or near infrared telescope or a radio telescope, it is possible. You can install radio telescope, near infrared telescope and optical telescope on ground-based observatory. But if you like to install a X-ray, gamma ray, ultraviolet, millimeter, far infrared, right, X-ray, then you have to go above your Earth atmosphere. That means you need a space observatory, and that is the need of space observatory. And most of you know there are many space observatory nowadays we have. Those are Einstein X-ray Observatory, IRAS, IUE, Compton Gamma Ray Observatory, SWIFT, Hubble Space Telescope, which is very famous, right? Cosmic Background Explorer, Rosette, etc. There are numbers of space observatory nowadays we have with different scientific objective. Okay, so that is the reason why we need a space observatory. Now Uh, uh, do you have any idea about the first astronomical? But I want to mention one more point here. If you like to observe a optical photon, then you need a optical telescope. If you like to observe a radio photon, then you need a radio telescope. And technique of all these telescopes, okay, structure or optics of all these telescopes are different. It is not same because energy ranges are different. So you cannot use a optical telescope to detect your radio photon. You cannot. Okay, you never. So that is the reason why we need different kind of telescope: X-ray telescope, ultraviolet telescope, gamma ray telescope, like that. And in our class, we will be discussing only about the optical telescope because of limitations of time. Okay. So, do you have any idea about the world's first astronomical observatory? Do you have any idea? Do you know the name of world's first astronomical observatory? You see, this is the people consider this as a early astronomical observatory. It is name of this observatory is Stonehenge. All of you know this is Stonehenge. Now you can ask me why we should call it as an observatory, because you see, because we are tracking the sun and moon in their seasonal excursion. Okay, if you track the sun and moon, you see these are pillars, hens. It is a shape of hens, right? The shadow of this pillar moving in different direction, and the length of this pillar is also sometimes decreasing and sometimes increasing at different seasons. Okay, so from that seasonal excursion, you can find out, you can predict about the different seasons like monsoon, winter, summer. It is like that, and people use this Stonehenge for basically for cultivation purpose. So it was in England in 2000 BC. It is very old, right? Stonehenge. This is, we consider it as a first astronomical observatory. So now after that, most of you already know about this Ptolemy. He's a mathematician basically. Basically, he is a mathematician, but he used to do astronomy also. In old days, most of the mathematicians, they do astronomy because actually, I can say what I can say. Applied mathematics is nothing but astronomy, right? Because to do astronomy, what you need geometry. You should be very good in geometry. You should be very good in mathematics. Then only you can do astronomy. Otherwise, not. You should be very good in trigonometry, right? Otherwise, not. So Ptolemy in 100 AD, he was in Egypt. What he has, he made a Earth-centric model, complicated Earth-centric model. What he predicted that in our solar system, our Earth is at the center, and all other planet, including Sun, is moving around the Sun. It is not true, but in 100 AD, I can say it is a great achievement in 100 AD. Okay, at that time we have nothing, so it is a great achievement. So after that, Aristotle, in 384 BC, he was from Greece. He moved one step ahead. He predicted a geocentric universe. Okay, he made a model of the universe, and in that universe model, our Earth is at the center. He also predicted that stars are perfectly spherical, but Earth is not. Then after that, in 476, you will be very happy, that is Aryabhat. Aryabhat, he is from Bihar, Nalanda. Okay, he is from Bihar, Nalanda. So by using he's a very great mathematician and astronomer, right? By using trigonometry, by using different shadow method, okay, he calculated the circumference of our Earth, and he found that the circumference of our Earth is nearly 39,968 kilometers. He also predicted that our Earth is spherical, and this value, which is calculated by Aryabhat in 476 BC, it is you can say it is almost accurate. And from today's calculation, we know that the value of circumference of our Earth is nearly 40,030 kilometers, which is very near. And he also predicted that apparent rotation of the celestial object was due to the actual rotation of our Earth, which is 100% correct. And he also predicted that, he also calculated, not predicted, he also calculated that the sidereal day is 23 hours, 56 minutes and 4.1 seconds. Now the question is, what is sidereal day? If you calculate your time with respect to sun, that is solar time. If you calculate your time with respect to stars other than sun, with respect to some other star, it should not be sun, then we consider that time as a sidereal time, and that day is a sidereal day. Our Earth has spin motion. Also, it is revolving around the sun in 365 days. So roughly, you can say that our Earth is moving every day. Our Earth is moving 1 degree ahead. So the difference of 1 degree is nothing but 4 minutes. So that is the reason why length of the sidereal day is 23 hours, 56 minutes and 4.1 seconds, right? So next one is Copernicus. You know, he's a Poland. See, so for the first time, he made the solar-centric model of our planetary system. And after that, this famous fellow Tycho Brahe, he is from Sweden. In 1546, he devoted his whole life, this fellow Tycho Brahe, he devoted his whole life for observing the position of stars and planets in the sky. He has a notebook. In that notebook, he make different figures, and in that figure, he put the position of stars and planet in daily basis. Today, what is the position? Tomorrow, where will be the position? Day after tomorrow, where will be the position? He has devoted his whole life to do this kind of stellar observation. And this Kepler, 1571, he was a German fellow. This Kepler, he was the student of Tycho Brahe. Kepler was the student of Tycho Brahe. So when Tycho Brahe died, this Kepler got the Tycho Brahe's notebook, where all the position of stars were kept, right? Then what the Kepler go through the notebook, and he spent at least 2-3 years to study the different position of the planets in our solar system. And after that, he framed these 3 famous law of planetary motion. First one is elliptical orbit. Next one is related to time and area. Third one is orbital period and semi-major axis, right? So you can say it is a very good achievement, but this Tycho Brahe, he was also tried to make some laws for planetary motion, but he could not. Why? Because this Tycho Brahe considered that our planets are moving around the sun in a circular orbit, right? That was the mistake done by Tycho Brahe. But Kepler, instead of circular orbit, Kepler considered it as an elliptical orbit. So after that, he got all these 3 laws. So now you know this very famous fellow. He is the father of modern astronomy, Galileo, right? He invented in 1608. For the first time, he invented the telescope and observed the moon. For the first time, he observed the moon with his telescope and began the modern age of astronomy, right? And purposely, I put one sentence here. Measurement was more important than philosophy. If you look at your history, in old time, most of the scientists, at that time, actually, there were no concept of scientists. All of them are philosophers, basically. They are philosophers. They have different philosophy. And most of them, they are very conservative in nature. they always believed only their own philosophy. So to get the truth, to know the truth at that time, measurements were more important than philosophy. So in my first class also I mentioned that in 18th century the European philosopher, they told people, they published that you never know what is there inside a star. There is no way to know what is there inside a star, what is happening inside a star, how the star is made of. But when 1857 that Fraunhofer, he took the spectrum of sun and other star, and after subsequent analysis of that spectrum by Kirchhoff and Bunsen, they came to know that at least the outer layer of our sun is made of gas which are available on our earth. So now you understand, at that time measurements were more important than philosophy. Nowadays also measurements are more important than philosophy. We have numbers of hypotheses, but if you cannot prove your hypothesis by using experiment, then you cannot convert that hypothesis to a theory. So for that you need measurement. If you go for measurement, then you can convert your hypothesis to a theory. So it is very important. So Galileo, what Galileo has done, he has observed the phase of Venus, craters on the moon, moons orbiting around the Jupiter, as well as sunspot. And these are nothing but, you see, these are nothing but craters in the moon. All of you know about that. So now we'll be discussing. It is 7:41, so we'll go a little bit more. So after 5 or 10 minutes, I'll stop. So most of you already know about the telescope, but again we'll refresh our knowledge just for a fun, nothing else. Okay, all of you know we have different types of telescope. So now you may feel that we are a primary class student. It is not like that. It is not like that. Levels are different. They will understand all these things in a different way. Now we'll understand all these things in a different way. Okay. So so you see, this is suppose this is the ray diagram of a telescope. This is my telescope, and this is my main mirror. Main mirror means, suppose there is a star, the starlight incident for the first time, starlight in this system, starlight incident on this primary mirror first. Okay, after that primary mirror reflected back that rays, and after that it will incident on the secondary mirror. And when secondary mirror reflect back those rays, you may put one tertiary mirror, and then it will be reflected by the tertiary mirror. After that, it will be converged at equivalent focal length of all these three mirrors, and in that position, in that focal plane, you can put your eyepiece to see the object, or you can put your detector for imaging purpose, or you can put your spectrograph for spectroscopic purpose, right? So this mirror we call the first mirror, where a starlight incident first, that mirror we called as a primary mirror, and people denoted it as a M1. Okay, secondary mirror, this is your secondary mirror. This secondary mirror we sometimes denote as a M2. Okay, these two are the you can say this is the optics generally we are using in a reflecting telescope. Okay, this is a reflecting telescope. If you go for refracting, then instead of mirror we will be using lens. Okay, so there are three different types of telescope we have. First one is refracting. In refracting telescope we use lens. Okay, and all the laws of refraction will be allowed or applied. Next one is reflecting telescope. In reflecting telescope we will be using the laws of reflection. There are two different kind of reflecting telescope. One is Newtonian and another is Cassegrain. We'll discuss later on. And third one is catadioptrics. What is this keta dioptrics? Okay, keta means two, dioptrics is coming from optics. So in refracting telescope, we are using only one optics, that is only refracting optics. In reflecting telescope, we are using only one optics, that is reflecting optics. But in catadioptrics, we will be using both reflecting optics as well as refracting optics. That means we will be using both lens and mirror. All the small telescope, most of your in most of the college and university, they have small telescopes nowadays. And there are very famous company, that is Meade and Celestron. That Meade and Celestron, they used to make this kind of Schmidt-Cassegrain telescope. If you look at this kind of telescope, you will see on the top of the tube there is a lens. On the top of the tube there is a lens. We call that lens as a meniscus lens. That lens we use to remove the aberration. Okay, after that, in lower part there will be objective, that will be objective mirror, then secondary mirror, then there will be some other optics. Okay, this Schmidt-Cassegrain and Marcus-Cassegrain, generally these are very small class of telescope where we use both lens and mirror. Now you see, but nowadays in the globe, people are not using refracting telescope. Around the globe, people are using only reflecting telescope. Why? If you go for refracting telescope, then what you have to do? You have to polish and grind both sides of the lens. But if you go for a mirror, if you go for reflecting optics, in a mirror, you have to polish and grind only one side of the mirror, right? No need to polish and grind both sides of the mirror. Okay, I want to I'll give you one example. I was very much involved with 3.6 meter Devastal optical telescope. I was the in charge of observatory control system as well as optics. Okay, so could you imagine the total cost of our that is India's largest telescope? Okay, 3.6 meter Devastal telescope, optical telescope, cost at that time in 2009 and 10, it was around 300 crore. And out of that 300 crore, could you imagine, we spent nearly 170 crore only for the mirror, primary and secondary mirror. So you cannot imagine, it is quite costly. Okay, it is quite costly. And that telescope, that 3.6 meter telescope, it is made by a Belgium company. Name of that company is Amos. Okay, Advanced Mechanical and Optical System. And mirror was made by Alzos. Okay, mirror was made by Alzos, and both the mirror made of zero door material. Okay, zero door material. And now, by using that telescope, 3.6 meter Devastal optical telescope, you can go for optical as well as near infrared. Okay, JHK up to 2.2 micron you can observe. Starting from 350 nanometer, you can go up to 2.2 micron in that telescope. That means you can cover optical and near infrared. Okay, so that is really very powerful telescope, and active optics technique we are using in that telescope. But I'll discuss about all those things, what is active optics and adaptive optics. So that is the reason why we go for generally reflecting telescope. So if you go for refracting telescope, then your price will be double, because you have to polish and grind both the surface. Then cost will be around 300 crore. So it is very costly, right? Also, to hold you in a telescope tube, it will be very easy for you to hold a mirror, but it will be very difficult for you to hold a lens. It is not very easy, right? So now you see, there are different kind of reflecting telescope based on the basis of your focal plane. We'll be discussing one by one now. So this is my primary mirror of the reflecting telescope. Rays are incident on the primary mirror. After that, rays will be convert. It will be meet at the focal plane. It will be meet at the focal plane. and this is nothing but your focal length. This is nothing but your focal length, right? So now image will be formed in this focal plane. So now I can put my detector, or I can put my spectrograph for imaging or spectroscopy in this focal plane. And this focal plane, this focal length you are getting only for the primary mirror. This focal length is only for the primary mirror. There is only one mirror. So this kind of telescope we call as a prime focus telescope. Prime focus telescope, because you are using the focus only for the primary mirror. And the next one, you see, generally we call this as a Newtonian focus. This is Newtonian telescope. What is that? This is my primary mirror. After that, after primary mirror, we are using another secondary mirror. This is your secondary mirror. So rays reflected by the primary mirror will be again reflected by this secondary mirror, and it will be focused somewhere here. Now you can put your eyepiece or you can put your detector in this focal plane to see the object or to record the image. Now you see, this is your telescope tube and images are formed inside the telescope tube. Now it is not very convenient for us to, during the time of observation, you have to go, what you have to do, you have to go inside the telescope tube and you have to put your detector inside the telescope tube. It is not very convenient. It is very difficult to use this kind of prime focus telescope. So that is the reason why people after prime focus telescope, people are using this kind of Newtonian focus telescope. In Newtonian focus, you see, your rays are diverted from the telescope tube to the outside, but it is also on the top of the tube. Still, it is not very robust. It is not very convenient. But after that, you see, this is Cassegrain focus. Generally, we call it as a Cassegrain focus. Nowadays, around the globe, most of the telescope, they are using this kind of focus. This is Cassegrain focus. This is your primary mirror. This is your telescope tube. This is the bottom of the telescope tube. This is your primary mirror. Rays are incident on the primary mirror, reflected back by the primary mirror, then again reflected back by the secondary mirror, and rays will meet at the focal plane. The focal length of this focal plane will be the equivalent focal length of primary and secondary. It will be 1 by f1 plus 1 by f2, right? So now what you can do, you can put your eyepiece here in this focal plane, or you can put your detector, or you can put your spectrograph here in this focal plane. Now it is a very robust telescope. Now you see, it is just the bottom of the tube, so it is very convenient for you to put your eyepiece. It is very convenient for you to put the spectrograph or detector. So that is the reason why people are using this kind of Cassegrain focus. So this is the primary mirror. At the center of the primary mirror, there is a hole. At the center of the primary mirror, there is a hole, so that the rays reflected by the secondary mirror will pass through and it will focus at the focal plane. Okay. So there are two more focus still people are using. This Nismat is very famous nowadays. Generally, our 30-meter class telescope, in 30-meter class telescopes also, people they will be using this kind of Nismat focus. What is Nismat focus? You see, this is your primary mirror, this is your secondary mirror, and this is your tertiary mirror. So it will be very so actually in case of 30-meter class telescope, at the same time we will be using number of instruments to observe a particular object. There may be an imager, there may be a spectrograph, there may be a optical field unit, there may be some other instrument also. Okay, so what generally people will be doing, people will be arranging all those instruments in a tray like this, in a circular way, in a circular tray, and rays will be in this tertiary mirror, by using this tertiary mirror, what you can do, you can use a half silvered mirror. By using that, what you can do, you can divert this ray in different direction, in 2 direction, in 3 direction, in 4 direction. If you can divert it in 2 direction, then in both the direction you can put 2 instruments. Okay, so simultaneously you can do photometry as well as spectroscopy. Definitely you will be losing some amount of energy because you are dividing one energy into 2 different ways, but it is 30-meter class telescope, so it has tremendous power, so no need to worry. We can go for this kind of niche-mark focus. So this is coude focus. Nowadays people are not using this kind of coude focus, but initially people are using this kind of coude focus. What is coude focus? I'll tell you. This is your primary mirror, this is your secondary mirror, this is tertiary mirror. After tertiary mirror, we are using numbers of mirror here. Why? You see, suppose one of you are interested to do some high resolution spectroscopy. Okay, suppose you have a high resolution spectrograph, and you may be aware that you cannot keep your high resolution spectrograph in an open environment. If you put it in open environment, then it will add some noise. It should be in a temperature control environment, and temperature should be, variation of temperature should be very less. So it will not be possible for you to keep your high resolution spectrograph in the observing floor. So what you have to do? You have to keep your high resolution spectrograph in a chamber, temperature control environment, and you have to divert the rays from telescope to that temperature control room. So suppose this is your room. By using this mirror, what you are doing, you are simply diverting the rays to the spectrograph. So this kind of focus, now we call it as a coude focus. But nowadays people are not using this kind of focus, because you see, instead of this arrangement, nowadays you can use simply a optical fiber. Just put a optical fiber, connect that optical fiber to your high resolution spectrograph, and you can easily go for your high resolution spectroscopy. So no need to use this kind of your coude focus. So now we'll be discussing about the telescope property, but telescope property, it will take time. So I'll just introduce telescope property, and for today we'll be stop here.
So can I ask a question? I mean,
yes, sure.
In this slide, if we put a secondary mirror inside a telescope tube, will it not reduce the amount of light?
Yes, sure, it will reduce. Certainly it will reduce. So actually nowadays nowadays we are using RC Cassegrain telescope, and I'll discuss about that RC Cassegrain telescope little bit later, and then your confusion will be, I think it will be clear. Definitely you are absolutely right, it will reduce the number of photons. So okay. In actually that RC Cassegrain telescope, we try to reduce the size of the secondary mirror as much as small. Yes.
Okay, another question. I mean,
yes.
When we can put a, I mean, you were saying spectrography.
Yes.
Is it like a spectrometer? I mean,
yes.
Are you putting a spectrometer to watch the spectrum of a star?
Yes.
Like this.
Yes. After that, you can put a CCD for imaging purpose. Record the spectrum.
Okay, we can take the picture of that spectrum.
Yes, but okay. If you go for low resolution spectroscopy, then there is no issue. You can put your low resolution spectrograph in your observing floor. It does not require any temperature control environment. But if you go for very high resolution spectrograph, suppose you are observing a very faint star, your exposure time is suppose 2 hours, 3 hours, 5 hours, then you need this kind of temperature control environment. In that case, initially people are using this kind of coude focus, but nowadays this just put a optical fiber and that will solve your purpose. Yes.
Okay, thank you.
Yes. Any more question? I want to take
sir, I have a question.
Yes, please.
Like for these spectrographs, we don't like. I tried because we have a 10-inch made telescope, and I was trying to find out a spectrometer for that. But
Yes.
such spectrographs are not really available in the market.
What is the size of your telescope?
10-inch
10.
mid telescope.
Okay, okay. I may help you. I may help you.
Okay.
I may help you. Yeah, I may help you. Definitely, I'll help you. No need to worry.
Okay.
I'll help you. So it is 10-inch telescope. At least you can observe 6-7 magnitude star easily, right? You can observe. You can have some practice, right?
Yeah.
It will be helpful. Yes, I'll help you surely. Yes. Any more question? Because if I'll start this, then it will take another 1 hour. So I won't like to start. I want to
another clarification
Yes.
I want to make. I
Yes.
mean,
Yes.
I think it is the Aristotle first who introduced the geocentric model. I think. I mean, he was before the Ptolemy. I mean, he
Okay,
was
maybe, but
He
yeah,
was-
I am
yeah, you
using
have-
some encyclopedia. I am
yeah.
getting all these
It is
story from
384
encyclopedia.
BC. I mean, it is written. It is 384
384, yes, and
So-
Ptolemy is 100 AD.
AD. Man, he came later than I think.
Okay,
Ptolemy came
Anno
later.
Domini, right? Anno Domini, BC, before Christ. Okay, let me check. Yeah, I'll check it. I'll check it. It may be. It may be. I have collected all these things from encyclopedia, nothing else. Okay. Maybe. Yes. Yes. Any more question? Yes. Any more question regarding my first previous observational astronomy 2 also we can discuss if you have any question regarding that 0 point atmospheric extinction and all these things, threatening and all these things. If you have any question, we can discuss now.
Sir, I have one question.
Yes, please.
This is space telescope, these are available like Hubble Space Telescope. Does it use visible astronomy?
Yes. Optical image also you can have from Hubble Space Telescope. Yes.
Then correction should be not necessary, I think.
Yeah, correction is that 0 point correction and atmospheric extinction correction is not required. Yeah, you are right. Absolutely right. That correction is not required because you are observing using a space telescope. That is not required. Yes.
It is required only on the surface of Earth.
Yes. If your telescope is ground based, then only you have to go for this atmospheric correction and 0 point correction. Otherwise, not required. Yes.
Thank you, sir.
Yes, absolutely right. Yes. Any more question?
Yeah, sir. This relationship between extinction and
Yes.
this reddening.
Yes.
And it's like you have written out this this
3.2.
there is factor of 3.2.
Yes.
So
somewhere you will find it 2.1. It is an empirical relation.
Okay. So does it depend on which direction you are looking at the?
Yes. Absolutely.
Okay.
If you are looking towards the galactic center direction, it will be very high. Okay, your extinction will be very high. I have mentioned your extinction in that case is 1.2 or 1. You can say 1 magnitude per kpc. But if you look towards the galactic center direction, it will be very high, really very high. You cannot imagine. It will be very high. Okay, so that is the reason why it is a challenging task to observe the galactic center. It is a challenging task, and already one point it is very clear to you that if your wavelength is increasing, then extinction is decreasing. So that is also one of the reason why people are using radio telescope to observe towards the galactic center direction, right? Because extinction is less. That is one of the reason. I think before 2-3 days, I think you have already seen one image of M87, center of M87. That is orientation of the magnetic field. Orientation of the magnetic field of that central object which is available at the center of the M87. So it is, I can say it is a tremendous, it is a great achievement for EHT. So now we see, now we know about the direction of the galactic magnetic field in M87, center of the M87. So it will tell many things about the central object. So it is really very interesting. Yes, any more question?
Sir, you mentioned that this extension, atmospheric extension, we should try to observe stars which are like have
Standard star.
yeah,
A0 type star, like
No.
Vega star.
No. About the angle, like the angle should
Yes.
not be more than 60 degrees.
60 degrees.
But like if you try to observe Polaris, like we observe it.
Yeah, I understand.
So for that, I think the formula we should be using that the second.
You see, for color correction, there are not only single formula. I put only one formula, but you will find many formulas, 3-4 formulas, and you have to go through all 4 formulas, and you have to adopt a single one. So if you go for color correction, then your accuracy will be high. Otherwise, you see, you are not going to do any variable star photometry, so no need to worry. You just go for your no need to go for color K2. You just correct it for K1. That will be enough for you. Okay, no need to worry, because if you go for variable star photometry, then only that is required. Okay, suppose you are observing a brown dwarf. It is very faint. Brown dwarf is very faint. So in case of brown dwarf, if you are doing brown dwarf photometry, then you have to go for that color correction. Okay, otherwise it is not required. Is it clear? Yes. Any more question? Any more question we can discuss now? I have little bit more time today. Yes. If no question, then I can stop here.
How accurately a polarization can we measure with these telescopes?
Which telescope?
So say small telescope like 1 meter class telescope and all.
Okay. You see, in Nainital we have 1 meter, and we have one polarimeter there already kept. So by using that telescope, you can go up to at least 14-15 magnitude. You can go easily. You can go 14-15 magnitude. So error will be your below 3 sigma. And the polarimetric accuracy, you see, instrumental polarization for 1 meter and that M pole, it is very less. Instrumental polarization is, I think, 0.02. Instrumental polarization is very less, so no need to worry. You can go for that.
Okay.
You can go up to 14-15 magnitude. Yeah.
Okay, sir. Can you suggest? I mean, if we want to buy a telescope in our institute, I mean,
yes.
What type of things? What should be the aperture like this? We should look for, and what else we should buy? I mean, to do some.
Yeah. First, I want to ask you one question. What is your budget? How much?
Yeah, I mean, I work in a college, so a budget will not be much. Maybe 2 lakh.
Yeah, within 2 lakh, you can. Within 2 lakh, I can suggest you something. No need to worry. I can suggest you. Now, I think it will be difficult for me to suggest something straightforward. But if you personally, I'll talk to you, or you just send me a mail. My email ID is bimanjmedi@gmail.com, or you can use biman@aries.res.in, or you can use biman@guwahati.ac.in. So we'll talk, and I'll suggest you something which will be very fruitful for you.
Okay,
so before I think 3-4 months, I have suggested one set of telescope. There is a institute at Guwahati, that is Institute of Advanced Studies in Science and Technology, ISST. I have suggested Professor Saikia sir is also there in that group. So I have suggested some very good telescope, and they have already bought. And there is another institute, that is CIT, Central Institute of Technology, that is also in Assam. So I have also suggested some telescope there. So I'll suggest some good telescope for you and good instrument. By using those, you can. But by the way, what is the sky condition in your college area? What is the sky condition?
Yeah, I mean, there will be a lot of light pollution and
yeah, that is the main issue. You see, with the astronomer, we didn't fear of your air pollution. We always fear. Our main fear is light pollution. There should not be light to do astronomy. That is the reason why generally we all astronomer move towards the jungle, forest area. Okay. Yes.
Okay, and what else we should buy? You should buy a spectrograph and
I don't suggest to buy a spectrograph. Initially, you should buy a imager. You should buy a imager. Just you can go for imaging. You can observe some variable star, right? You can make a variable star light curve, which will be very exciting for you as well as for your student, right? Observe Vega. Already you know the color index of Vega is 0. Observe Vega. Try to verify whether the color index of Vega is 0, and if 0, why the color index of Vega is 0. This kind of small project, these are very interesting, and you can go for that. And later on, you see, if the size of your telescope is small, then I don't suggest you to go for spectroscopy. For spectroscopy, we need a very big telescope, right? Because you need more energy. Then only you can have a very good signal to noise ratio, and you can do something. Otherwise, it is not possible. Okay, but later on, I'll suggest. Yes.
So better way, like a small telescope with good mount is preferable for institutes.
Yes.
So like mount is also very important.
Yeah. I'll devote 2 or slide on telescope mounts also. So in that class, I think it will be clear for you. So generally there are different kind of mount. So I'll suggest you to go for polar mount. Then I should suggest you to go for Cassegrain focus. There is a Galilean focus also, but I'll suggest you to go for Cassegrain focus. That will be good for you, right? And I'll suggest you to go for catadioptrics. That will reduce the amount of aberration. So your image quality will be good then. Yes.
Okay, thank you.
Yeah, thank you very much.